Um, yeah. Next we have another recorded talk towards generic type checking implementations in Haskell. And well, I will list all the potential speakers this time. I'm not sure who is recorded. Nikolai, Anastasia, Vladislav, Diana, and Ekaterina.
Hello everyone, my name is Nikolai Kudasov, and together with my collaborators Anastasia Smirnova, Vladislav Deryabkin, Diana Tomilovskaia, Ekaterina, Maksimova, we're going to present our work in progress on an approach to generic type checking in Haskell. So, type systems are central to programming languages and proof assistants, but are also widely used in all kinds of formal systems. Many different type systems exist, and for each system, usually a few type checking algorithms can be found. Implementations of these algorithms, however, are typically bound to a particular formal system and are not easily available for use, tuning, or modular extension in other systems. While it is usually not difficult to implement a basic type checking algorithm, ensuring that it is correct, efficient, extensible, and user-friendly is not always easy. A generic and modular implementation of type checkers may lower the entry barrier and make different type system ideas more accessible. A language agnostic type checking library could, in theory, incorporate many of the best practices and make it easier to experiment with the typing rules, get decent error messages, error localization and recovery, and perhaps even get a nice integration with things like language servers to automatically enable features like showing type on hover or providing type context for the current cursor position. We believe that such tooling for prototyping type systems is possible, and in this project we simply start by working with the two well-studied approaches to type checking, which is bidirectional typing and Hindley-Milner-style type inference. The main idea of bidirectional typing is to replace declarative typing judgment with directional judgments for type checking and type synthesis. This makes the flow of information more explicit in the typing rules, revealing that what would normally be hidden in the implementation. The usual flavor of bidirectional typing allows for local type synthesis, that is, when synthesizing a type, we only rely on the information about the subterms, not about the outer context. This typically means better error localization, as there is no spooky action at a distance that may cause a typing error. However, this may also mean more user-specified annotations required. That said, there are many flavors of bidirectional typing, and it can even be combined with type variables to enable non-trivial connections between remote parts of the code through unification. A basic implementation of bidirectional type checking, again, is often straightforward. However, there are multiple implementation-specific nuances that impact integration with other components of a formal system down the road. For example, how to properly represent and work with the typing context and how to propagate information properly or efficiently, how to properly cache typing information when computing or modifying the code, and given declarative typing rules, how to determine when to check and when to synthesize types. For the latter question, the answer is given, or an answer is given by the Fenning recipe. The recipe was described by Dunfield and Fenning back in 2004, and then refined and broadened recently in 2021 by Dunfield and Krishnaswamy. The recipe is a way to convert a system of declarative typing rules into a bidirectional type system, and the recipe does not necessarily provide the final truth or the final system, but instead is to be considered as a starting point for an actual practical system, depending on what your rules are. The set of bidirectional rules that are produced by the Fenning recipe has some good properties. For example, it is mode correct, and which roughly means that we definitely can derive a recursive algorithm that would not get stuck on something during type checking. It is also small and annotatable. Moreover, the type annotations that are required by this new bidirectional system are lightweight, meaning they are only in the places where they're really needed, but they're also predictable, meaning that programmers know which parts of the program require annotations. The recipe is outlined again in much detail in 2021 paper by Dunfield and Krishnaswamy, and what we believe is that this recipe is subject to automation in a language agnostic way, and to the best of our knowledge, this has not been done before.
Another well-studied type system is that of Hindley-Milner, which enables synthesis or inference of parametrically polymorphic types for local definitions via lead binding. This algorithm requires first-order unification of type variables and, for efficient lead generalization, a level-based implementation due to Didier-Remy, which is not widely known. Additionally, extending Hindley-Milner with type classes, subtyping, or general constraints further complicates the implementation. Implementing generic Hindley-Milner or bidirectional typing should be relatively straightforward once we have a generic representation for abstract syntax with binders, which is we likely have thanks to FreeFoil. FreeFoil allows to generate an efficient, intrinsically scoped abstract syntax with binders from a given signature that is presented by a Haskell data type with two parameters. The first parameter, named scope, corresponds to subterms with exactly one binder, like body of a lambda extraction or lead binding. The second parameter, named term, corresponds to plain subterms like two subterms of a function application or the first subterm of a lead binding. Type constructor AST is provided by the library and is similar to the fixed point combinator that automatically adds variables and binders in the correct places. The phantom type parameter n is statically tracking the scope of each term. This is a feature of underlying FOIL approach, which is in turn is a type safety mechanism on top of the RPR, which is an efficient implementation of the bound-direct convention for bound variables, which is used by Glasgow Haskell compiler as well as Agda. The library implementation of FreeFoil provides convenient template Haskell helpers that work well with parser generators like BNF converter, making it easy to develop prototypes for small object languages. And importantly, for us, FreeFoil comes equipped with efficient generic capture warning substitution and alpha equivalence checks.
Now, by default, FreeFoil works with just one signature, which is a problem when syntax of terms and syntax of types is mutually recursive. For example, types may be used in annotations for lambda expressions, and terms may be used in dependent or refinement types. Now, while the actual current implementation of the library provides more flexibility with that respect, truly mutually recursive definitions like this are not supported at the moment. So when using the FreeFoil for type checking, we have to consider what situation we're in and make a decision. In particular, if we have only simple types, that is, there are no binders that are allowed to bind type variables, then we simply use the FreeFoil on terms and treat types as built-in things that are not of concern to the FreeFoil. However, if we do have binders for type variables, but they are separated, so we have binders in terms that bind variables that have variables for values, and we have binders in types that bind variables for types, then we can just use FreeFoil on the two definitions separately and use it this way. Now, if terms and types mix, then instead of applying FreeFoil, which will not work in this case, we are combining the syntax of both into a unified syntax. Now, this is a shortcoming of the FreeFoil, but first of all, want to point out that hypertypes library, which is defined by Yer Chuchim, offers a generalization of data types a la carte approach that supports mutually recursive definitions. However, combining it with the foil or any other intrinsic intrinsic scoping mechanism is maybe an interesting research direction, but it would require significant changes to the user-facing interface. So we stick with the free foil for now and just embrace the unified syntax. That said, we think that such a unification of terms and types also has a few advantages. In particular, if we unify the syntax, at least at the end of the parser, this simplifies the grammar, usually at least. It makes sure that all of the template Haskell machinery still works well. And because the separation is delayed, the error messages that the user gets are typically better. Instead of unexpected syntax, the user can get a proper context of using say, a type variable where a regular variable or the term level variable was going to be used. And of course, if in the future the object language is supposed to grow and incorporate features such as dependent types or refinement types or features like scope type variables or anything else, then it is very easily done. You do not need to do anything extra. Now, the foil distinguishes scopes of terms via phantom type parameter. And one of the main features of the foil is zero cost syncing. It is always safe to coerce a term into a scope that is larger. However, this is of course not true in the other direction, right? When exiting a local scope, we have to check that whatever term, if we want to coerce to a smaller scope, we have to make sure that our term does not have these extra variables, does not make use of that. So in the type system, that means that in a non-dependent setting, for example, when we're inferring the type of the body in a lambda abstraction or a LED binding, we then need to unsync, ensure that the type is non-dependent. And so intrinsic scoping and mixing of terms and types demands this check for us. But also, because we have to perform this check, it contributes to, again, a better error message when we sometimes misuse accidentally type and term variables.
For now, we are testing the waters and getting comfortable with the free foil. We have implemented a Hindley-Milner type inference and are working on the efficient level-based generalization before generalizing the entire algorithm. Similarly, for bidirectional typing, we have explored system F with the unified syntax and unsyncing of types, and are now looking for a proper generalized interface. Our project is available on GitHub and is partially documented. In the near future, we plan to generalize our implementations and sketch automation of the Epiphany recipe for bidirectional typing. We also aim to adapt HMX to a language-agnostic variant based on freefoil. Finally, we would like to implement several test type checkers using our library. This is all. Thanks for tuning in. Now we will be open for questions or comments on our work.
Great questions when we have the speakers online.
Hello again.
Hey, can you hear us again? Looks good?
Yes.
Okay, great. Right. So I had two questions. Now let me actually think of the second one. Right. So with you mentioned that terms and types are use the same namespace in your approach, right? And then you said that also helps with generating better error messages. But yeah, so for some languages where these really are separate namespaces, then you would not be able to implement those languages. Is that correct?
Do you mean if you allow users to define their own like types and values and mix those namespaces?
Yes, when those two namespaces are truly separate and users can access either one and there's no shadowing.
Right. I don't think that. So I think that can be handled. What we are talking more about is mixing the syntax of both terms and types, not necessarily the namespaces. Now, by default, of course, the foil will use the same sort of namespace for local variables, but you can still disambiguate them further when they're used as types versus when they're used as terms, I think. Yeah, I don't I understand the question. I don't immediately see sort of a big problem with that, but I also don't have an immediate good solution, I guess.
Okay, good. Other questions? Otherwise, I was able to think of the other one again. At the very beginning, you mentioned that you have multiple use cases for this, also better error messages, and also maybe IDE integration and so on. Which in the end, those parts, especially for maybe the IDE integration, should not even be that dependent on how the type inference is implemented, right? Like
Exactly, yes.
Could be that there's some general metadata that is completely independent of the inference implementation, and maybe even of the term type. Not sure. But yeah, did you think about separating these two concerns, or is it just very convenient with basing both of them on free foil? Do you see some synergy between that?
We have been thinking about this with some other students also. There isn't any progress to report there yet, except that I can say that there is this query-driven architecture for compilers, and in particular in Haskell, I believe there is a library called Rock that sort of dips into that. And so when developing a type checker, it's good to have that architecture in mind already, on the one hand. And the way that you would use that would depend, I think, on a specific, or at least in general, on a class of the type checking algorithms that you're about to use. And that would also depend on so there are two things: the interface to the type checking algorithm, and which is both about the going from the typing rules to the actual algorithms, but also in breaking apart the type checking algorithms into smaller pieces or smaller methods that can be used more incrementally by the language server, so that you do not have to recheck the entire source code every time, for example, right? And also, to be able to do things like show me the type on hover, you don't need to check anything. You just need to store the information already somewhere.
Yes,
so there's a
exactly.
separate question of how you store your ASTs such that this information is readily available and inspectable, how you annotate them with type information, location information, how you mix that. So I guess those are the slightly separate things, but they are still connected to each other. At least I have not fully figured out for myself how you could completely separate those concerns. So our plan is to try and do that for maybe specific algorithms. First, implement them with this free foil approach, just as in non-query driven way, then do the same with the query driven approach and see how we can properly extract the interfaces such that they are in the most configurable, so that we have the most tunability or configurability out of that. I hope that answers the question.
Yeah. Query-driven, that sounds very appropriate. Okay, great. I see you have some further thoughts in that direction as well. Do we have other questions? Okay, then let's thank the speakers again.
Thank you.